manufacturing engineering, automated testing, and power supply design. Following the presentation, we'll have a live Q&A with Terry and George. You can submit your questions at any time during the session using the chat box on the right-hand side of your screen. Thank you so much for joining us, and with that, I'll hand it off to Terry and George for the presentation.
Hi everyone, and welcome to today's webinar focusing on the topic of BMS, or battery management systems, and highlighting the L9963E, a 14-cell lithium-ion battery management IC from STMicroelectronics. My name is Terry Yao. I work in product marketing in the automotive products group at ST, specifically supporting the SPS, or Smart Power Solutions products division, and I am based out of ST's Livonia, Michigan office. Here is the agenda for today's webinar. We'll start by looking at the main objectives for battery management systems, followed by the key enabling functions from the BMS IC. Then we will dive into the L9963E, looking at its many features and architecture, along with the companion transceiver device, the L9963T. Finally, we'll conclude this webinar with a look at all the collateral offerings for this BMS family, as well as potential applications. Let's start by taking a look at the main objectives for battery management systems. First and foremost, in any battery-operated device, safety is a top concern. We want to maintain the battery pack in a safe operating condition to prevent fires and other disasters, and thus need to monitor for any faults that may occur. This involves accurate measurements of the cell voltage, current, and temperature, along with isolation detection measurements and redundancy measures. Once the safety aspect is covered, we then want to maximize the performance and efficiency of the system. To maintain high levels of performance, we need a way to accurately assess the level of charge in the battery. And we also want to optimize the efficiency to extract the maximum value out of the battery pack. All of this is dependent on the accuracy of the cell measurements. Finally, we want to extend the service life of the battery pack to as long as possible. And to that end, we need to prevent any operating conditions that may shorten the battery life. This requires accurate and reliable cell balancing, as well as effective thermal management in the BMS. This slide illustrates in detail how the BMS objectives are met with a monitoring IC. The four key BMS functions that help us achieve these objectives include cell voltage measurement, current measurement, cell balancing, and thermal monitoring. For cell voltage measurement, accuracy is critical for determining the state of charge. This helps prevent any overcharge or over-discharge in the battery pack. Likewise, current measurements also need to be highly accurate, and this is linked to the fuel gauge function as well as protection against short circuit conditions. Cell balancing is critical for maximizing the battery capacity and service lifetime, and finally, thermal monitoring contributes to safety of operation as well as service lifetime. Now let's take a detailed look at the L9963E and see how its features and operation address the key BMS objectives we talked about. The L9963E is a 14-cell lithium-ion BMS IC from ST. The device can manage anywhere from 4 to up to 14 cells connected in series. There's also the option to daisy chain up to 31 of these devices. So depending on the cell chemistry in use, that will give you a battery pack voltage in excess of 1500 volts. This device can manage both low voltage battery packs as well as high voltage battery packs. Cell voltage and current measurements are supported by this device. You can see in the diagram here, the cells are connected on the left. The balancing FETs are internal. Balancing current is supported up to 200 milliamps per channel. You can connect an external resistor to limit the current during balancing. The cell measurement ADCs are integrated as well. A unique and beneficial feature of this device is that there is not a single ADC, but rather 14 ADCs with one dedicated to each cell input. The important benefit of having the dedicated ADCs is that we can make highly synchronized, high-precision cell measurements. It's very accurate in that when you issue a command to sample the cells, you can sample all the cells simultaneously. You can also measure the current at the same time that the voltage is measured. And if you have a high voltage battery pack with multiple devices connected in daisy chain, the only desynchronization from the lowest cell measurement to the highest cell measurement is the time that it takes for the measurement to propagate up the daisy chain. In the example of an 800 volt battery pack, that propagation time is on the order of 2 microseconds. Current measurements are made with continuous time sigma delta ADCs. There's a wide range in filtering time that can be applied to the converters. And the main advantage of this is that the converted value represents the average value over the sampling window. So any noise present on the signal will be averaged out and filtered. The longer sampling window you can tolerate, the more noise attenuation you can achieve in your measurement. This is another differentiating feature with our solution. Another highlight of our device is its accuracy performance. Recall that measurement accuracy is a critical parameter in BMS modules due to its impact on virtually all aspects of battery management. For measurement accuracy, we specify plus or minus 1 millivolt initial accuracy with a maximum accuracy specification of plus or minus 1.4 millivolts when accounting for the effects of drift due to soldering or aging. The accuracies are specified over the entire operating temperature range of the device and vary according to the cell chemistry in use. There's a slide later in the presentation which details the measurement accuracies to be expected based on the usage case. Current sensing with Coulomb counter is integrated as well. This is done through an 18-bit sigma delta converter with 17 bits plus sign for both positive and negative current measurements. There's a 0.5% error on the current sense amplifier circuitry. Hence, you can make highly accurate current measurements on this device as well. In terms of communication interface, there are two communication interfaces built in. There is a standard 4-wire SPI interface at 6 megabits per second. So in the case of a 48-volt battery pack, without the need for multiple devices connected in daisy chain, the typical architecture would have the MCU being connected directly to this 4-wire SPI port without any need for isolation. In the case of high voltage battery packs, there is the need to be isolated from the chassis ground domain. So for that, we have the isolated communication interface shown here, with the ISO H being the high port and the ISO L being the low port in the system. Both mono and bidirectional daisy chain configuration are supported in this device. In terms of the bidirectional daisy chain, you can also have a dual ring configuration. And this basically enables you to communicate from the bottom of the stack upwards or the top of the stack downwards, so that in the case of a fault anywhere in the chain, you can still communicate with the device. And this concept is illustrated in more detail in one of the slides later in the presentation as well. For cell balancing, you can balance all 14 cells at the same time, maybe not using as high a current as the 200 milliamp maximum balancing current per cell when balancing simultaneously, and this is mostly due to thermal limitations. For balancing, there is both a manual mode as well as a timed mode to perform the balancing. External balancing is also supported if higher balancing current is needed. There are 9 GPIOs present on this device. Some of these can be used for NTC monitoring or temperature monitoring. In addition, there are also 14 bytes of user-accessible NVM integrated in the device. And finally, because this device was initially designed with an automotive application in mind, it is ACQ qualified per automotive standards, and it is also compliant with the highest level of functional safety, which is ASIL-D, which is typically required in safety critical applications, such as in EV applications. Focusing more on the architectural benefits of our implementation, by having dedicated ADCs, desynchronization is definitely a key benefit. The 14 cells are measured at exactly the same time. Less than 2 microseconds desynchronization time can be expected in an 800-volt battery pack. Safety is another key benefit. Having dedicated ADCs per cell leads to a fully redundant conversion path via the adjacent sigma delta ADC for each cell. In case of ADC failure in any cell, that cell can then be converted by an adjacent sigma delta ADC. The slide illustrates in more detail the difference in desynchronization between our implementation and that which does not have dedicated ADCs per cell. With the dedicated ADCs, all voltage and current measurements can be taken simultaneously, resulting in a significant reduction in the total conversion time. This approach also greatly improves the accuracy of the readings by providing a single snapshot in time of the voltage and current readings in the battery pack, thus eliminating any inaccuracies resulting from the delay from the first measure cell to the last measure cell. With the dedicated ADCs, we're able to tolerate a longer conversion time per cell, resulting in BOM cost savings for external passive filtering components. Additionally, the continuous time sigma delta converters also have 8 programmable filter options, with a longer filtering time leading to better noise attenuation. Here is a more detailed look at the cell measurement architecture. The cells are configured in pairs, cell N and cell M+1. Connected to ADC-N and ADC-M+1. We have the capability to cross-check these two ADCs against each other, and they're also connected to independent voltage references that can also be checked against each other. So if there's ever a fault detected on one or the other of these measurement paths, the faulted channel can be swapped and measured on the good channel. If you have a fault on the channel N+1, cell M+1 can then be measured by ADC-N. You've lost your synchronization capability now because you're no longer able to make those measurements at the same time, but at the least you can still see what's happening with the cell that's connected to the faulty channel. So that's definitely another important benefit of this architecture from a safety and redundancy perspective. Another unique and beneficial feature of this device is its accuracy performance. Shown here in more detail for different operating conditions and cell chemistries. Here you see a range that's typically representative of an LFP chemistry, up to 3.2 volts. Initial conversion accuracy is specified to be in the plus or minus 1 millivolt range over the entire operating temperature range. Additionally, we have characterized the accuracy also taking into account the effects of drift, whether due to aging or soldering, and the 1 millivolts becomes 1.4 millivolts at the end of the life of this device. This accuracy performance is among the best solutions on the market. This is the L9963T device, which is part of the L9963 family of BMS offerings. The T here standing for transceiver. So this is a general purpose SPI to isolated SPI transceiver and serves the function of creating a communication bridge between the devices located on different voltage domains. Using a high voltage battery pack, such as in an EV application as an example, the L9963T is used as the communication interface between the chassis ground domain and the high voltage ground domain. This device supports both transformer and capacitive isolation, and is also compatible with 3.3 volt and 5 volt logic. Note that the same isolated SPI interface is also built into the L9963E device. Here's an application example with the L9963E and T devices. Here, multiple BMS ICs are daisy-chained to monitor a high-voltage battery pack. The devices are connected in a dual ring configuration, which allows for a higher level of communication integrity, where recovery can be guaranteed in the event of a single open failure in the communication wires. The L9963E device supports bidirectional dual ring daisy chain configuration so that you can communicate from the bottom of the stack upwards or from the top of the stack downwards, such that in the case of a fault anywhere in the chain, you can still communicate with the device. This configuration consists of 2 SPI peripherals on the MCU, as well as 2 L9963T transceivers on the master PCB. A number of development boards and kits are now available for evaluation of the L9963 BMS family, including the device eval board, an MCU discovery board, a battery holder kit, and a SPI to ISO-SPI dongle for communication between the MCU and the BMS IC in the different voltage domains. Additionally, all supporting documentation, including the datasheet, application notes, safety manual, etc., are also available either for download online or provided on request. Since batteries are everywhere around us, there exists a wide range of target applications for BMS ICs. In the automotive space, the introduction of EVs have led to a significant focus on BMS modules, and there are also a large number of industrial applications, including energy storage, power tools, line equipment, just to name a few. The type of BMS IC employed for these different applications depends on the specific system requirements, such as pack voltage level, cell configuration, cell chemistry, accuracy specifications, etc. And within ST's BMS product portfolio are offerings that address many of these applications in both the automotive and industrial sectors. And that concludes the presentation portion of this webinar on BMS ICs. I hope you found it helpful and informative. Additional information on our BMS product offerings, along with data briefs, data sheets, application notes, and other collaterals can be found on our website at st.com. Thank you.
Welcome to this part of the webinar where we will talk about the transformers that Würth Elektronik has for battery management systems. My name is George Slama. I'm a senior application and content engineer based in Watertown, South Dakota. You may be wondering what transformers have to do with managing batteries, but as we heard earlier, it's very important to manage batteries at the cell level of 3.3 volts, even though the complete pack may be at 400 volts, 800 volts, or a higher voltage. The battery management ICs all operate at lower voltages and are usually ground referenced to the module that they monitor, yet they must be able to communicate with other modules and the master controller, which all have different ground references. For this to happen efficiently, the battery modules must be able to communicate without a ground reference. A battery module consists of a group of individual cells, and each cell needs to be monitored. The L9963E can monitor up to 14 cells. Using a system that's not ground potential based, but rather differential signal based makes it easy. The system that has been developed uses a serial bus with differential signaling between the modules and the controller in a daisy chain fashion, which can also be connected in a complete loop for redundancy. The signaling is based on the serial peripheral interface, SPI, which is one of the most widely used interfaces between microcontrollers and peripheral ICs. However, SPI is ground-based and uses at least 3 wires, but usually 4. Therefore, a transceiver circuit was created to convert the single-ended data lines into a differential signal using twisted pairs of wires. This transceiver can be a separate IC, or it can be integrated with the BMS IC. The ISO SPI interface uses differential signaling on a balanced pair of wires, where neither wire is grounded. With this configuration, the common mode noise impressed onto the wires by external EMI noise is nearly identical on both wires, and the transmitted differential mode signals remain unaffected. The recommended ISO SPI interface uses transformers to magnetically couple and electrically isolate the signal between the devices. This shields each device from common mode voltage swings created by the system noise while transmitting the information across the dielectric barrier, which bridges the different ground potentials. This is the same technique used in twisted pair Ethernet. Furthermore, the electrical isolation allows the battery modules and packs to be interconnected despite the large DC voltage differences between them. A transformer is used to bridge the isolation barrier, but it must be selected for the appropriate DC standoff voltage for the voltage of the battery pack. A transformer offers excellent isolation and high immunity to bulk injection currents and to common mode noise. The transformer does have some specific design challenges. The signal portions requirements are straightforward in that they are similar to those of an Ethernet transformer with regards to inductance, insertion loss, and frequency response. However, the challenge is the isolation needed to meet the creepage and clearance for safety at high voltages in the battery pack. Normally, communication transformers fall under IEC 62638-1, but that standard only applies to systems up to 600 volts. Additional standards like IEC 60664-1 then apply. Furthermore, there are specific vehicle standards for high voltage that must also apply. In all cases, the creepage and clearance distances can be much greater than a typical signal transformer. The usual result is a larger transformer size, sometimes just so that the terminals are far enough apart. The WE-BMS transformers come with up to 15 millimeters of creepage and clearance, as I will show you in a moment. In order to have a long life, the transformer must be carefully designed not to have partial discharge. A particular problem with devices that operate at high voltage potentials is partial discharge. Partial discharges are localized dielectric breakdowns that are often caused by voids in solid insulation. When a high voltage is applied across an insulation, the charge will distribute across the barrier according to the dielectric constant of the material or materials. If the material is solid and homogeneous, the distribution will be even. But if there's a void or an air pocket, the charge distribution will be uneven and will concentrate in the void because the dielectric constant is considerably lower in that spot. This will lead to a breakdown in the void, resulting in carbonization and an expansion of the void over time. This is partial discharge, which is not a complete breakdown, hence it's only partial. Eventually, it will lead to failure of the insulation over a long period of time. To ensure the long-term reliability of the insulation system, Würth Elektronik carries out a partial discharge test in accordance with IEC 60664-1. The test involves applying a predetermined voltage at a higher level than working voltage for a short period of time, typically 5 seconds, and then reducing it to the working voltage plus some margin for about 15 seconds to get a measurement. The test voltage is determined by the insulation class, whether it's basic, supplementary, or reinforced. The test passes if the coulomb count is below a limit value of 10 picocoulombs. In the bottom right is the definition for creepage and clearance. The creepage, in red, is the shortest distance between two conductive parts measured along an insulating surface. Any irregularities in the surface, like a gap, must be a minimum size depending on the material class to count as part of the path. Clearance, in green, is the shortest distance between two conductive parts through air. The main difference between WE-BMS transformers and other parts is that we can meet the creepage and clearance distances requirements through physical distance. The physical distance requirements are met through an innovative housing design that forces and guarantees the distance, yet does not significantly increase the size of the device. You can see in the cross-section where the wire weaves through a maze. A subtlety is that this maze must have specific dimensions to meet the standards. The WE-BMS transformers offer the highest physical creepage distance, increasing the safety and reliability of the system despite the small footprint. Every transformer module comes with an integrated common mode choke designed to match the application and increase common mode rejection. This means one less component to handle. It reduces board space and increases the reliability with fewer connections. The Würth Elektronik product portfolio offers transformers with and without a center tap. In addition to the integrated common mode choke in the transformer module, the center tap contributes to suppression of common mode interference. For this purpose, a bypass capacitor is connected to the center pin, which provides a low impedance path to the ground for common mode interference and thus diverts it from the IC. This leads to an improvement in the ISO SPI performance. Here's an example of the styles of transformers offered. Many are available as two transformer and common mode chokes in one package, simply because, as you saw earlier, there is one communication pair coming into the BMS IC and there's one pair leaving it. Combining everything into one package simplifies the purchasing, handling, and assembly. There are also individual transformers offered for other types of applications. The WE-BMS transformers are fully tested up to 6400 volts DC with working voltages up to 1500 volts DC, making them ready for the next generation of high voltage battery packs. They use high quality, fully insulated magnet wire to meet the reinforced insulation requirements in a reduced volume of space, and they are fully tested for dielectric strength and partial discharge. Here's an example of a screen capture from a partial discharge test. The purple area at the bottom is the coulomb count, which is well below the 10 picocoulomb line seen in the center of the screen. The chart on the left shows that the dielectric test is performed first at a high voltage level for a short period of time, then the voltage is reduced to measure if there's any partial discharge. Here are a few layout guidelines. As always, keep traces as short as possible to reduce the noise pickup because they act as antennas. Place the transformer as close as possible to the connector, ideally within 2 centimeters. The IC also should be close to the transformer within 1 or 2 centimeters. Although not shown here, there will of course be some ESD devices and some EMI capacitors between the IC and the transformer, and between the transformer and the connector. With multiple layer PCBs, there must be enough clearance between the transformer, the connector, and other traces and the ground planes, at least 4 millimeters, but perhaps more depending on the working voltage and any applicable standards. Here are the common electrical properties. Just remember that the transformer and common mode choke cannot be separated, so the values apply to the combination of the two devices. If the turns ratio is not mentioned, it's 1 to 1. Pin 1 is marked by a dot, and the numbering is counterclockwise, just like an IC. In summary, the new WE BMS series contains a transformer to isolate the signals and a common mode choke in order to help filter common mode noise. The design from Würth Elektronik provides a much higher physical creepage distance than other offerings and in a small package size with many low-profile options. Dual transformer design helps to further reduce component count and handling, and all the parts support the ISO SPI interface, such as used in BMS systems, and they're all fully AEC 200 qualified for automotive applications. That concludes my presentation. I return to the moderator, and then we can take any questions that you might have at this time.
Hey, thanks, Terry, for the handoff, and thanks, George, and thanks, Terry, for your presentation as well. So we already have several interesting questions, but I want to let our audience know that there's still time to submit those questions. Use that chat box on the right-hand side. Terry, George, you ready to answer some of these questions?
Yes.
Ready.
Awesome. All right. The first one is asking, and I think this was directed for Terry, is what is the cell measurement range on the L9963E device?
Yeah, so cell measurement range is in the range of 0.1 volts to 5 volts. So basically the device measures positive voltages up to 5 volts. So one thing to note is we do have a new family of BMS devices that are starting production very soon. Actually, the L9963